We have seen that for a conservative vector field, that means for a field for which curl is equal to 0, the line integral is path independent, and the line integral over a closed curve is equal to 0. And Stokes' theorem is generalization of this result, and it says that the line integral of a vector field f over a closed curve C is equal to the double integral of the curl of f. Before we explain this, let me start with some introductory example. Consider the very simple vector field f arrow at the point xy to be such vector field A plus bx plus cy, the first component, and let me write it as a column, and the second component will be a, b, c, d plus ex plus fy. And let us consider the line integral of this vector field along the following rectangle. In some position xy, we make a step of size delta x to the right and a step delta y to the up, and we form this rectangle. This is the curve C, and we want to compute integral of this vector field along this closed. This little circle means that it is an integral over a closed curve. This vector field can be written as a sum of 6 simple vector fields. A0 plus bx0 plus cy0 plus 0d plus 0ex plus 0fy. And now, if we check the curl, namely whether derivative of f2 with respect to x is equal to derivative of f1 with respect to y, then for a constant vector field, yes. So this contribution gives 0 to this integral. You can forget it. This is also 0 because when differentiating f1 with respect to x, with respect to y, we give 0. So this second component or second part, second contribution gives nothing to the final integral. This one will give something. Yes, we will have to take this. This has again 0 curl, so 0 contribution to the line integral. That will give something, and this will give again 0. So all we have to do is to consider vector field with components cy, ex. Well, when we start with the first segment, then y is constant and x runs from x to x plus delta x. So our vector field can be just cy ex. So instead of this, we will integrate this because this gives the same contribution, the same result. So f1 is cy which is constant along this line, and integrating a constant is equal to the constant times the length of the integral, the difference of the limits. So if we multiply by dx, we have the integral over this line. Then, over this line, we have x is constant, so what is important is only f2. f2 is ex, is equal to x plus delta x. And we integrate this constant for y from y to y plus delta y. But integrating a constant is the constant times the change of the limits. Now, the third segment. This is very similar to this one, but we go to the left, so dx will have the opposite sign, so we have minus, and y is not y plus, but y plus delta y. And finally, this left-hand side particular segment, when integrated over this, gives a similar contribution as, as this one. But now x is only x, not x plus e to x, and we go downwards, so we write minus. When we expand this multiplication and this multiplication, then cy delta x with plus with minus cancel each other, and ex delta y minus ex delta y cancel each other, and what remains is delta x times delta y times e, delta x times delta y times minus c. So we can factor out delta x delta y, and we have e minus c times delta x delta y. And if we evaluate the third component of the curl, which is f2 dx minus f1 dy, then f2 dx is e, and f1 dy is c. So you see, e minus c is the third component of the curl. So we can write it as curl of f, third component of that. If we have a two-dimensional vector field, we can think of this vector field to be in a horizontal plane xy with the third component f3 equal to 0. And then the third component of the curl is this difference, f2 dx minus f1 dy. So this is the third component of the curl times, and delta x, delta y is some area, let's call it delta s. And if we consider the oriented area, the oriented surface element, then delta x delta y has the normal in the z direction. So we could call it as delta x3 as the third component of some vector. And this begins to resemble this, you see, curl f times ds. If curl f is a vector, and if we consider ds as a vector, then this dot stands for dot product, the scalar product, and this is the third contribution to the scalar product. We will come to this later. Well, and now if we have a large circle or curve, then let me sketch it in an extra picture. Then we can cut this into a large number of small rectangles, and the line integral over the entire region can be written as the sum of line integrals, each along one small rectangle. Because if you consider a large area like that, and if you divide it this way, then going zack, 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 plus zack, 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 then this common edge is run twice, each time in opposite orientation. So if we add these two line integrals, then this portion, one going to the left, one going to the right, annihilate each other, and the result is equal to the line integral over the entire circumference. And in this way, we can join all these neighboring pieces, and in the end, this is equal to the line integral over the entire curve. Another explanation might be this way. If we have a closed curve like that, then we can compute the line integral FDR along this closed curve. And this can be written as f1 dx plus f2 dy. Let me write it as f1 dx plus 0 dy plus 0 dx plus f2 dy. And then let's have a look at the first contribution first. Then x, well, we start here at sum A, and we go with x from A to B along the lower part, which we can call a graph of a function y1 of x. And then we go from this rightmost point to the leftmost point along this curve, and let's consider this curve as a graph of a function y2x. So the first part, the first integral, is integral from A to B f1 evaluated at some x that goes from A to B, and at some y, which is given by this lower part by the function y1. dx. And then we go from here to here. That means minus because dx is negative if we decrease. And now f1 is evaluated at some x and at some y2. And similarly, for the second integral, if we consider this line divided by these 2 points to the right-hand side and left-hand side part, and if we call this curve as a graph of a function x is x2 of y, and the left-hand side as x is x1 of y, then y goes from some c to some d, and we evaluate f2 at x2 y, y, dy, And then going downwards means minus integral from C to D. Well, actually, there would be plus integral from D to C. But if we write from C to D, if we swap the limits, we must write minus. And now F2 is evaluated at the left-hand side part x1, y, y, dy. And now here we integrate the same function, well, not the same function, evaluated at different arguments, but we have the same limits, so instead of difference of integrals, we can write integral of the difference. And let's write minus, and we start with 2 minus 1. But difference of two function values, f1 at y2 minus f1 at y1, difference of two function values can be written as an integral of the derivative. If we consider the derivative with respect to y, and then we integrate over y from y1 to y2, which is a function of x, then this integral of the derivative is the difference. And then we integrate over x. And we can do the same for these two terms. Here we have again difference of f2 at two different arguments, x1 and x2. And the difference of this function values can be written as the integral of the derivative. If we take f2 and differentiate with respect to x and integrate with respect to x in good limits, this time from x1 to x2, each as a function of y, then this integral is the difference of these function values, and we integrate over y. But integral from C to D, and then integral from x1 to x2, this is a double integral of some function, integrated over this whole surface. And here, integral from a to b, and integral from y1 to y2, corresponds to integrating this expression over this two-dimensional domain. In these two integrals, the order of integration is reversed. But both are integral of some expression over this area, and it minus or plus integral of some expression over the same area. So we can write it as a double integral over the surface S of f2 dx minus f1 dy. And when we write the name of the integration domain, capital S, then dx dy, there is no, the order is not important. And that's exactly what we wanted to show. You see, the line integral of the vector field f over a closed curve C this loop, is equal to the double integral over the area for which the loop is the boundary. And this is the third component of the curve, you see? And the slight generalization from the plane situation to the space situation gives that if we do this for xy plane, xz plane, and yz plane, then we get three contributions of this form. Once with index 3, then with index 2, and then with index 1. And if we add these three contributions, these three products, then we get the dot product of curl of f with the first component here, the second component here, and the third component here, times ds, where ds is the vector with components ds1, ds2, ds3, with elements of the surface having the normal parallel to the first, second, and third coordinate axis. So this is a nice generalization of our old result. Then when this is 0, then this is 0. Well, and for non-conservative vector fields, when the curve is not 0, then the line integral over the closed curve is equal to this double integral.